design and construction of post-tensioned transfer plates. What is the objective of this presentation? To define what are the transfer plates by way of giving you some examples. Pictures of transfer plates in construction. Design requirements of transfer plates. And in what way the transfer plate design differs from traditional floor design. And review some practical design procedures. Introduction and application of extended thin plate design method. This is the design method which traditionally was used on the thin plate, and I like to discuss a little bit about its applicability and in what way it can be improved. Then a comparison of the thin plate design approach with the thick plate, because transfer plates are typically very thick. We talk about shear deflection, which could be important. Now, what are transfer plates? When you have a heavy load on a slab, and the slab has to transfer the heavy load to wall and columns that support the slab. So it is the magnitude of the load which determines whether you need a transfer plate or not. Span to depth ratio of transfer plates is typically between 10 and 4. I mean span to depth. Now, how does this compare with an office building and a residential? In an office building or residential, the span to depth ratio could be 50-45. This is 10 to 4. So transfer plates are much thicker than traditional floors. For typical multi-story building, the slab thickness could be as much as 3.5 meters. 3.5 meters, this thickness. And the spacing between the columns can be 10 feet, 15 feet, 20 feet, depending on the application. Here are some examples of transfer plates. On the upper left, note the multi-story levels of something that looks more like residential, all supported on a few columns in order to provide space below for a totally different structure. Again, here we have a thick transfer plate at the bottom left, which separates the multi-level footers superstructure from a different arrangement below, and there is a similar situation on the diagram to the right with the transfer plate here. More examples: transfer plate multi-level on selected columns. Likewise, here you have a thick slab bottom left supporting two towers, and again here on the right you have transfer plates at the bottom supporting multi levels. This is an example in Hong Kong where the transfer plate is supporting again commercial and parking structure below, with support layout which is farther apart than the levels above the transfer plate. In this case, the transfer plate is 4.5 meters in thickness, about 57 meters above ground. That is almost 15 feet in concrete thickness of the slab. There are two examples under construction: few supports at the bottom, multiple above. And here you have the transfer plate. Likewise on the right, construction is in progress, few columns, but multitude of supporting elements above the transfer plate. One construction challenge is the support of the weight of the transfer plate on the construction over typically high level above the ground. The weight here of this plate, sometimes 20-30 meters or more above the ground, is a challenge during casting of concrete. This is something which we will discuss in the following slides as how it can be handled. Another example of a very large transfer plate for this, again, a large superstructure. The two images are views of transfer plate reinforcement. What you see is the going up and down, the ducts of grouted post-tensioned members configured to raise the load here at midspan and dump it, deliver it to where the supports are. Another example of the transfer plate. Now, the typical quantities obviously vary greatly with the span, with the weighted supports. But what is not uncommon is to have 10 to 15 kilograms per cubic meter, which is 0.6 to 1 pound per cubic foot of concrete, and rebar about 170 to 120 kilogram per cubic meter, or 10.6 to roughly 14 pounds per cubic foot. I have here additional examples, a view of transfer plates. In both cases, bonded tendons are used. Bonded tendons are the preferred option. This is one of our projects in Macau, which is a transfer plate here, 3.5 meters, which is about 11 feet, 38 meters, which is about 120 feet above the ground, supporting the superstructure. Apart from the design considerations, construction of 3.5 meters, say about 12 feet, concrete plate at the required height is a challenge, or was a challenge. The construction scheme became the primary consideration for structural design of the transfer plate. The plate was constructed in multi-layers to handle the self-weight for its height, its weight over this height. in multi-layers. The first layer, which is 1 meter, about 3 feet, was cast on support from the ground. So the bottom layer was supported on the ground and cast. The bottom layer was designed to support the weight of 2.5 meters, say 8 feet, chopping that formed the balance of the plate thickness. So the slab thickness was broken into 2 layers. The bottom layer was cast first on ground support, but reinforced to carry the weight of the upper layer when it was hardened and cured. Together, the combined plate thickness, the bottom and the top, supported or designed to support the weight of the entire floor building. Now, this figure illustrates the forms on ground support. These are the forms on ground support and the 2 layers. The tendon installation includes the lower level as well as the entire depth. You have the lower level tendons and also the tendon of the entire, both put in place. Figure B here is completion of casting of the lower layer. This lower layer is designed to carry its self-weight and the weight of the slab above it when it is being cast. This figure shows the completion of the work by casting the top layer and removal of the ground support. Here you still have ground support, there the ground support is removed. These 2 images are construction views of the transfer plate we just looked in the previous figure. This shows at the bottom the post-tensioning of the lower layer, and this is the post-tensioning of the bottom and top layer. A technician on the right is adjusting the post-tensioning. The wall forms on the left gives the depth of the transfer plate, gives the impression of how deep it is. This is the depth of all concrete. Computer model shows the 3.5 meter plate with 1.5 meter added column drops. We have column drops here, 1.5 meter, which together they support a multitude of walls above the transfer plate. This is the 3-dimensional view, and here I have the see-through model of that plate showing the arrangement of post-tensioning tendons. Now let us concentrate a little bit on design requirements. Like any other structural components of a project, you have the ultimate objective is serviceability and safety as far as the code is required, but obviously you want to have something economical for the client. The design differs from the common floor slab in the following respects. You have smaller slab span to depth ratio. That is span. Smaller should be span to depth ratio, typically between 4 to 10. Defines the application of thin plate theory, that is, basis of the common floor design, questionable. In commercial building and residential projects, the span to depth ratio is typically can be 40, 35, even 55. Here you have in the region of 4 to 10. So the slab is much thicker. Heavy concentrated loads call for special attention to shear design. Plate deflection due to shear, which is commonly disregarded in floor slab design, may become significant. It is very rare that in a residential or commercial building you consider shear deflection effect of the floor. Not here. Here it could be significant. When constructed in layers, like 2 or 3 layers, we also have had examples of constructing a transfer plate in 3 layers. Then the question of stress checks come up that should account for a locked value in stresses in layers that were previously cast. Special provisions are required for transfer of safe load from the layer above to the layer below at layer interface. At interface, you have to check the transfer of force so that the 2 or 3 layers will act together once complete to resist the load. Punching shear can become the governing factor, hence special attention to shear design becomes important too. For design requirements, the following demonstrates the application of the common computational tools to arrive at a safe, serviceable, and economical designs. The tools that we have for common residential and commercial, how can we use those in order to design this transfer plate? The figure shows elevation of member in bending. It breaks the member into regions marked B and regions marked D. All discontinuities, such as supports D, the mechanic at discontinuities where we have D, the load transfer, the mechanism of load transfer is somewhat different from the middle, where we typically apply the regular plane sections remain plane and the beam theory to determine the stresses. So here we need to pay special attention. So I first review the challenges in design of the transfer plate. Common floor design is based on plate sections remain plane. Plane sections remain plane. This is this region B. The region B. For roller support condition shown in the figure, I have roller support. The moment and shear axial remain the same irrespective of span to depth ratio as illustrated in parts D and E. What I'm trying to say is the demand. Here is the force demand. In this configuration, the force demand, which is bending and shear, will be the same as if it were thin plate or thick plate. It is the resistance that the member provides in accounting for the applied moment and shear which differs. The resistance mechanism of the member is influenced by its span to depth ratio. Here I show different span to depth ratios. For region marked B, the conventional design is used, this region. Regions marked D may require additional design consideration and detailing. The schematic of this region D is shown here. You have this block here. The application of load could be determined from the previous figure, which for a simply supported member is no different from thin plate. It is the transfer of this to the support in this region which is subject to closer consideration. One option commonly used is to assume that the actions here are transferred to the support by way of a strut action, a compression member and tension member, and calculate the compression force and the tension force and make sure that there is adequate strength in the member. The traditional approach is here on the right for common beam and slab construction, that you take the shear by stirrups. This can also be applicable here. There is no mandate that you have to use this strut and tie. This is also possible, but this one in the middle is more reflective of how this region is responding. Now, I am going to take you through one or two slides, some item which is not directly related, but it is important as a background information, and that is how the thin plate theory works, which is used for regular commercial and residential. In thin plate theory, you have a deflection as I have shown here, and you have a curvature of each piece segment of the plate as shown here, and that is commonly used in the software which is conventionally commercially available. It is based on thin plate theory. Thin plate theory is approximate when span to depth ratio is 10. Appropriate is 10 or more. It applies well for thin slabs. For thick plates with span to depth ratio less than 10, extended thin plate theory or thick plate procedure is more appropriate. The common assumption of plane sections remain plane leads to the deformation shown in this figure. This is based on plane sections remain plane, where the plate displacement is entirely due to its bending. Entirely due to bending, you would get this shape. Now, when plate aspect ratio is low, like I have here, that means the plate is thick, the arch action also becomes significant in carrying the load. This is the load transfer is not primarily to bending, you also have the arch action there. In typical transfer plates, the aspect ratio is low in regards to the contribution of arch action in load transfer. I have a thin plate here at the top right and a thick plate at the bottom, and I am showing you the different types of moment distribution. Why do I show different moment distributions? Because if the end supports are not on a roller, there will be an action due to the arch effect. The arch effect action would be more for the thick plate, like this. So this results in a bending. This force times its distance to the centroidal axis results to a bending moment. So the deflection and moment distribution will somewhat be impacted depending on the support configuration. By that I mean whether it is restrained or not restrained, and how much arch action will develop. I have here the moment distribution for larger span to depth ratio, which is condition in residential and commercial buildings, and then for low aspect ratio. The figures illustrate the load transfer mechanism of a plate with different thickness ratios. In thin plates, such as used in the shell of ships, that is very thin. Very thin. You have a span to thickness which could go to 100 or more, or aircrafts. The formation of tensile membrane forces reduces the lateral deflection. Now, this is something which is for your just information. It has no application in transfer plate. If the member is very thin, like aircraft skin, there will be membrane stresses even if the support is not fixed. In-plane stresses which reduce the out-of-plane deflection. This is background information, doesn't apply to concrete structures. It applies to metal structures, thin plates. For common transfer plates, however, having low aspect ratio, the precompression shown in B, there will be a precompression shown in B, reduces the demand moment. Now, deflection due to shear can become significant in thick plates. If you look at the support region, you have shear force, and the shear force is carried at the face of the support by distribution of shear stress and deformation of each of the elements on the surface. So this displacement gamma will result in shear deformation. Thin plates doesn't account for shear deflection, but Shear deflection can be conservatively estimated for, as shown in C, by this mechanism. If you want to estimate it. For uniform loads, an approximation of uniform distribution of shear stress over the section, the ratio of bending to shear deflection is given by this relationship. Bending deflection divided by shear deflection depends on span to depth ratio. This is based on this mechanism. So the larger is the thickness, the larger will be the ratio here. I have a diagram here which shows the shear deflection becoming of design significance in thick plates. Here is a span to depth ratio, and here is the ratio of the shear to now that is the moment to shear deflection of ratio of moment deflection to shear deflection. These the graph over this region is of no significance. It is just here for, I would say, just giving you a sense of variation. This is really the region we are dealing with. The graph indicates that the ratio of shear to moment deflection is not critical for common transfer plates with span to depth ratio 20 or less. This is span to depth ratio. That means we have far less than 20. This is where we deal with. So the range of application is really here. Now let us look at a design example. This is the project we dealt with in Macau. Shows the transfer plate at 3.5 meters and the see-through analysis model used. 3.5 meter thickness is the plate. Column drops are 5 meters. Pretty large column drops. The bottom layer was 1 meter. This was cast in 2 layers. And the 2.5 upper layer was designed to carry the weight of all 2 layers and the superstructure above it. Figure A shows the installation of entire post tensioning. You have ground support, post tensioning for the lower layer, and post tensioning for the upper layer. Figure B shows the support from the ground. It was designed, this stage was designed to carry the weight of the bottom layer only. The ground support was designed to carry the weight of the bottom layer only. Figure C shows the bottom layer fully cast, finished, and the top layer cast. This bottom layer carries the weight of both of them. When it comes to design, the stress distribution is this bottom layer is checked for bottom fiber stress F1, and then you have the upper layer. You will have new stresses here with a stress distribution different here, which will be F2, obviously will be more than F1 because you have the load above there. And when stressed, you have, in addition to this locked stresses, new distribution of stress due to weight of this over the bottom. And when in service you have a stress distribution, which I have shown at the bottom right, which adds up to the locked in stresses. So you have to trace the formation of stresses. The figure shows the states of construction and the distribution of design moment for each stage. The design targets to keep the extreme fiber tension stress at the bottom of the plate within permissible values. At the last stage, which is here, figure D, the extreme fiber will be the sum of the construction stresses and the applied load. Shear stresses generated at the interface of the first and second layer have to be calculated and designed for using dowels between the two layers. This image at the right shows the completed configuration with the load on the plate, the bending moment for the entire applied load shown here. The following schematic illustrates the concept of the computation of the interface shear. Under this bending moment, you have distribution of stress like this. You have compression at the top, you have tension at the top. If this is the layer, you can find the force at the top, which is the area above this separation line, and you calculate the area below. The difference between the area above and area below is the shear that has to be taken by this interface. So the difference between the two will be a force, and that force has to be transferred from one to the other, and I have shown it here by a shear force to be resisted by shear at the interface, which you have obviously shear friction, but it is common to put dowel between the bottom and the upper to resist that C, that force, which is the difference between the integral of this stress above the layer and that below the layer. I will conclude and with a couple of other figures of the construction stage. This shows again one construction stage, another construction stage. What you see here is a bottom layer of another project. This is the total layer. What did we cover? I talked about transfer plates definition application, talked about specific design considerations from low span to depth ratio, common for transfer plates. I talked about impact of positional fixity of supports. If the supports are fixed, you will have also some arching action which come into plate. in addition to moment. Talked about shear deflection, that in transfer plates, shear deflection could be a design consideration. Then I talked about extended thin plate theory for transfer plates. I showed a graph which talks about thick plate and thin plate deformation and bending moment. Went through an example of transfer plate using layered construction and gave some views, construction views, with the focus on tendon layout. The material I presented to you in this presentation was taken from a chapter of the book shown on the right. Thank you for listening.